I am Yang. I will describe a way to train a static image segmentation network that uses unlabeled videos. We call it Dynamic Static Bootstrapping, or DyStaB. When you look at this image, you see a random dot stereogram, nothing in it. But if something moves, then hopefully you can see an object moving within. This kind of experiment was used by Bela Julish in the 60s to prove that one can infer properties of the thing, such as motion and shape, without any need for semantic interpretation. There is nothing in this image that looks like a dinosaur. There's just salt and pepper noise. Yet, we can see and recognize the dinosaur. The goal of this step is to learn to segment objects without any semantic annotation, just by observing things moving. On the other hand, once we have learned an object, we have no trouble to detect and recognize it in static images. Our vision is unlike that of dinosaurs, whose amphibian system could only detect moving objects. This step uses video to seed static object detectors that can work on single images. As we detect more and more objects, conversely, the static model should act as a prior and improve the video segmentation, thus creating a virtuous cycle, which we call dynamic static bootstrapping. In this step, a dynamic model partitions the image into temporally consistent regions, which can be used to bootstrap object models for segmentation in static images. The static module then acts as a top-down prior to facilitate better motion segmentation. Next, we briefly introduce the two modulars and show how they reinforce each other in a synergistic loop. The dynamic module is based on the principle of information separation across different regions. Given an image, we have a prior of what motion fields are compatible with it. This gives a conditional random field, so how do we pick a point estimate? The idea of information separation is simple. An object is a region of the image whose motion inside is as informative as possible of the motion outside, and vice versa. In this example, if the region is bigger than the object, it will contain information about the outside. If it is smaller, the background will contain information about the motion of the object. Only if when we hit a correct boundary, the information exchange is minimal. This can be measured by a ratio of conditional entropies and can be minimized through adversarial impending. As a side note, for those familiar with the famous Montfaucon functional for image segmentation, it is exactly the opposite. In Montfaucon segmentation, one looks for the best explanation of the object using owning the image inside the object. This captures no context. However, in our case, we try to explain the inside of the object using its context, and we try to do the poorest job at it. Thus, contextual information separation. Since we have multiple frames in a video, we apply temporal regularization to ensure smooth segmentation. The dynamic model can segment moving objects in a temporally coherent manner. However, if the objects stop moving or are moving in a way that is not salient, the dynamic model may fail. This is where image intensity comes to the rescue. Our static model, bootstrapped from the outputs of the dynamic model, can segment static and partially moving objects. Its output can be used as a prior to regularize the dynamic model. The key to the success of the static model is to account for the uncertainty of the motion mask using the information measure computed during detection. For example, when the motion segmentation is much more confident than the prediction of the static one, as shown in the left, the static model will be bootstrapped with the motion mask. However, both models will have similar confidence when the motion field is noisy, as shown in the right figure. In this case, the update of the static model will be conservative. Once the static model is updated, it will be used as a top-down object prior to improve the bottom-up motion segmentation, thus forming the feedback loop. As the volume of thin videos grows, the performance of the static model also improves, growing left to right with the number of objects learned. Moreover, the static model can generalize to unseen objects even if they are not shown in the training videos. Thanks for your time. For more details, please come to our live session.